Hey everyone, welcome back. I just wanted to quickly say sorry about not uploading anything over the past month. I've been dealing with a lot of internet issues lately, and to be honest, I still am. But I'm doing my best to get videos out again. Thanks for being patient, and now let's jump right into the video. In this video, we're going to continue building our neural network class by implementing the train method. This training method includes support for mini batches, a dynamic learning rate, and binary cross-entropy as a loss function. We'll also dive into the gradient computation, figuring out how much each neuron contributes to the final error. And by error, I mean the difference between the actual value and the predicted value. Let's get started. First, we include the log.hpp file and the ssstream library. And here we say hash include log.hpp and hash include ssstream. We'll use log.hpp for logging training information to a log file. And string stream helps us build nicely formatted messages during training. Now let's create the train method. And here we say void train, and it takes const std vector double reference inputs. This is the data we use to train our model. Each input is a feature vector. And then we say comma const std vector double reference targets. These are the actual values or labels we want the network to learn. We compare predictions to these during training to compute the error. And then it takes double learning underscore rate. This controls how much we update the weights and biases in response to the error. A smaller learning rate means slower but more stable learning. And then we have comma size underscore t epochs, the number of times we go through the entire training dataset. Next, comma size underscore t batch underscore size equals to 1. Instead of updating the weights after every single input, we group several inputs together, like 8 of them, and update the model based on their average gradient. This is called mini batch training, which helps stabilize the updates and improve training efficiency. By default, we set it to 1. And the last parameter is comma bool verbose equals true. If this is set to true, we'll print training information to the console and also log it to the log file. This is helpful for tracking progress and more. Before we start training, we check that the number of input samples matches the number of target outputs. If inputs.size is not equal to targets.size. If they don't match, we throw a runtime error, because training wouldn't make sense if each input doesn't have a corresponding label. So here we say throw std scope runtime underscore error, and we pass in this message: input and target sizes don't match. Next, we make sure the training parameters are valid. The learning rate, number of epochs, and batch size must all be greater than 0. If any of these conditions fail, we throw a runtime error to prevent invalid or unstable training. So here we say if learning underscore rate less than equals 0.0 or epochs less than equals 0 or batch underscore size less than equals 0. And here we throw std runtime underscore error, and we pass in this message: learning rate, epochs, and batch size must be positive. Now we store the size of that dataset in a variable, size underscore t, dataset underscore size equals inputs.size. This helps us manage batching, loop over the data efficiently, and keep our code clean and readable. Here, we're capturing the current time to measure how long the training process takes. And we say auto start equals std scope chrono scope high underscore resolution underscore clock scope now. Now we're going to declare another variable, double total error equals 0.0. This will be used to accumulate the loss during each epoch, so we can print it and log it every 100 epochs. At the beginning of training, we want the model to learn quickly, so we start with a higher learning rate. But as the training progresses, we gradually reduce it. This helps the model fine-tune and converge more smoothly without overshooting the optimal values. This strategy is called learning rate decay, and it's a common technique to improve training stability and final accuracy. Now, we're going to declare a variable to store the base learning rate, double base underscore LR or base learning rate equals learning underscore rate. This is our starting learning rate, and we'll use it as the base value for applying learning rate decay over epochs. And here is the decay rate, double decay underscore rate equals 0.996. This controls how much we reduce the learning rate after each epoch. In this case, we decayed by about 0.4% per epoch. Now let's define another variable, double min underscore LR or minimum learning rate equals 1e minus 4 or 10 to the minus 4. This sets a lower limit on the learning rate to make sure it doesn't get too small and completely stop learning. Next, we check if verbose is enabled. If verbose, and if it's set to true, we print training information to the console and also log it to the log file. This helps us track progress and debug if needed. Inside the verbose block, we create a string stream, std string stream data. This lets us build a well-formatted training summary using the stream insertion operator like this. Finally, we print it to the console using cout and log the same message to our log file, std cout and data.str, and then l scope log, and we pass in data.str. Now we're starting the main training loop. For int epoch equals 0 and epoch less than epochs and plus plus epoch. The first thing we do inside the loop is update the learning rate using decay. And here we say learning underscore rate equals std max, and we pass in minimum learning rate, comma base learning rate times std POW, and we pass it decay underscore rate and epoch. We multiply the base learning rate by the decay rate raised to the current epoch. This reduces it gradually over time. And we use std max to make sure learning rate never goes below our minimum learning rate. So learning doesn't stop completely. Right after updating the learning rate, we reset total error back to 0. Total error equals 0.0. This makes sure we start fresh for this epoch and only accumulate the loss for the current path through the data. Now we're starting the mini batch loop, and we say for size underscore t batch equals 0 and batch less than dataset underscore size and batch plus equals batch underscore size. This loop lets us process the data in chunks or batches. Instead of feeding one input at a time, we update the model using groups of inputs. This is called mini batch training, and it's more efficient and stable than pure stochastic or full batch training. Inside the batch loop, we calculate the actual batch size. Size underscore t actual underscore batch underscore size equals std min, and we pass in batch underscore size, comma, inside parentheses, dataset underscore size minus batch. This handles the case where we reach the end of the dataset and the remaining samples are fewer than the batch size. So we take the smaller of the two. Now we create a vector to accumulate the gradients for the weights. Std vector matrix weight underscore batch underscore gradients. Then we loop through all the weights in the network and create a gradient matrix for each one with the same shape. And here we say for size underscore ti equals 0, I less than weights.size and plus plus I. And inside the loop, weight underscore batch underscore gradients dot in place underscore back, and we pass in weights square brackets I dot get rows and weights square brackets I dot get calls. These matrices will hold the sum of gradients for each mini batch, and we'll use them later to update the actual weights. Next, we set up the batch gradients for the biases. std vector double bias underscore batch underscore gradients, and we pass it layers.size -1. Since each layer except the input layer has biases, we create one vector for each of those layers. Then we resize each vector to match the number of neurons in its corresponding layer and initialize them to 0. And we do it like this. For size underscore ti equals 0, I less than bias underscore batch underscore gradients dot size and plus plus I. Inside the loop we say bias underscore batch underscore gradients square brackets I dot resize, and we pass in layers square brackets I +1 dot size and comma 0.0. These will store the sum of bias gradients for the current batch. Now we loop through each training example in the current batch. For size underscore t k equals batch and k less than inside parentheses batch plus actual underscore batch underscore size and plus plus k. Then inside the loop we run the forward pass. Forward, and we pass it inputs square brackets k. Next we get a reference to the output layer. Layer reference output layer equals layers.back. Before calculating the loss, we define a small constant. const double, and we're gonna call it epsilon equals 1e minus 7. This is used to prevent log of 0 during loss computation. We'll clamp the predicted values so they stay in a safe range between epsilon and 1 minus epsilon. Log of 0 is undefined in math. In practice, it gives us negative infinity, which completely breaks our loss function and the gradients that follow. That's why we clamp our predicted values between a tiny value like epsilon and 1 minus epsilon, so we never end up calculating log of 0 or log of 1 minus 1. In this project, we use binary cross-entropy or BCE as a loss function. But what is BCE? BCE is a way to measure how well our predicted probabilities match the actual binary labels, 0 or 1. The formula looks like this. Y is the true label, 0 or 1, and y hat is the predicted probability, and log is the natural logarithm. But why is there a minus sign in front? Because logarithms of values between 0 and 1 are negative. Without the negative sign, the loss would also be negative, which doesn't make sense because we want the loss to be a positive number that grows when our predictions are worse. So the minus sign flips the result and makes the loss positive. This ensures the model always works to minimize the loss, heading towards 0 as it gets better. This loss function is especially good for binary classification problems like ours, predicting a collision 1 or no collision 0. Now we loop through each neuron in the output layer. For size underscore ti equals 0, I less than output layer dot size plus plus I. This is where we apply the binary cross-entropy loss we just talked about. For each neuron, we'll calculate the loss and its gradient, that is how much this neuron contributed to the total error. And even though we currently have just one output neuron, using a loop like this keeps our code flexible in case we expand the network later. Inside the loop, we grab the actual target value and the predicted value for this output neuron. And here we say double y underscore true equals targets square brackets k square brackets I, and double y underscore pred equals output layer dot a square brackets I. We'll use both of these in the last function and to compute gradient. Now we clamp the predicted value to make sure it's within a safe range. Y underscore pred equals std min, and we pass in std max, and we pass it y underscore pred comma epsilon, and outside comma 1.0 minus epsilon. This makes sure y underscore pred never becomes exactly 0 or 1. Now let's compute the loss using binary cross-entropy. Here we say total error plus equals minus inside parentheses y underscore true times std log of y underscore pred plus inside parentheses 1.0 minus y underscore true times std log of 1.0 minus y underscore pred. This accumulates the BCA loss for each sample in the batch, so that at the end of the epoch, we can analyze the model's performance. Now we calculate the gradient for each output neuron. Output layer dot gradient square brackets I equals y underscore pred minus y underscore true. What this means? This is the derivative of the binary cross-entropy loss function when the output activation is sigmoid. When you combine binary cross-entropy loss and the sigmoid activation Their derivatives simplify to gradient equals to output minus label. So this line gives you the gradient for the output neuron, and we use gradients in backpropagation to adjust the weights and biases. Now we loop backward through the hidden layers to calculate their gradients. For int L equals, inside parentheses, static underscore cast, int layers.size -2, and L less than 0, and minus L. Layers.size -1 is the output layer, so layers.size -2 is the last hidden layer. We go backward through the layers until we reach the first hidden layer. Because layers.size is size underscore t, an unsigned type, and we're decrementing, converting it to int ensures safe looping backwards without underflow. Now we iterate over each neuron in the current hidden layer. For size underscore ti equals 0, I less than weight square brackets L dot get rows and plus I. Inside the loop, we declare a variable to accumulate the error signal. Double error equals 0.0. This error variable will hold the total weighted error that comes from the next layer and flows into the current neuron. And we loop through each neuron in the next layer. For size underscore tj equals 0, j less than weight square brackets L dot get calls plus j. And here we accumulate the error. Error plus equals layers square brackets L plus 1 dot gradient square brackets j times weight square brackets L and inside parentheses I comma j. Finally, we update the gradient for the current neuron. Layers square brackets L dot gradient square brackets I equals error times layers square brackets L dot apply activation derivative, and we pass in layers square brackets L dot z square brackets I, the pre-activation value of that neuron. And that wraps up this video. We have computed and stored the gradients for each input in the batch, but we're not quite done yet. In the next video, we're going to finish implementing the train method by accumulating the gradients over the batch and updating the weights and biases. The final step in completing our training loop. You can download all the project files, including the dataset, source code, and log files from my GitHub. The link is in the video description. If you are enjoying the series, make sure to like, subscribe, and turn on notifications so you don't miss the next part. Thanks for watching, and I'll see you in the next one.